Let's attack the system C too. Come with me. Have here the system C. This is a more complex system. We'll have to think more deeply into the system. But let's do it. We have here our system in the equilibrium position, okay? And we displace the mass by a distance x. We will notice a force here that is minus s times x? No. No, because this force acting on the mass is the force of just this spring. The mass is in contact with just this spring. This other spring up here is supporting all the system, all this system. But directly, the contact force acting on the mass is just the elastic force due to this spring below, and not necessarily the displacement of this spring below is the all x, okay? The spring above will have a displacement too. So we can identify this displacement of each spring as, for example, delta L1 and delta L2. Delta L1 being the displacement of the spring 1 and delta L2 being the displacement of the spring 2. So how can we relate our x, that in this case we cannot write the elastic force like that, but how can we identify, relate x with this delta L2 that is the actual displacement of the spring, and thus will be the amount of displacement coming to the elastic force that acts on this mass? Well, we can notice that ideal springs has no mass, okay? Ideal springs has no mass. Ideally, we have such a low mass that we can consider theoretically it to be zero. So this piece, this junction, for example, of springs has no mass, and if we write Newton's second law for this element, we will get that the mass of this element times the acceleration, since the mass is equal to 0, the force is also equal to 0. But we have here an elastic force due to the second spring, so this is this is S times delta L2 in module, and we have up here S delta L1, okay? So if the total force is equal to 0, it means that this force here is equal to the downward force too. And since they have the same factor S, the only way to these forces to be equal in module is delta L1 being equal to delta L2. So we can write that delta L1 is equal to delta L2, okay? But the displacement of the upward spring plus the displacement of the downward spring is the total displacement of the system, is our x, okay? So we can write also that delta L1 plus delta L2, that is equal to 2 times delta L2, is equal to the total displacement of the system, that is x. So we can write that delta L2 is x divided by 2. And if we write the total force now acting on the mass, we will get that the total force is equal to minus S times delta L2, that in this case is S times x divided by 2. And this is also the mass of the system times its acceleration. So we can identify this guy here as our K. This is the equivalent stiffness of this system of two springs, equal springs in series. And this is our little m. So we can conclude that the frequency of the system C is 1 divided by 2 pi times the square root of our k divided by our little m. In this case, our k is s divided by 2, and our m is simply the big M. So this is the frequency of the system C.